All right, guys. Good morning. So this is gonna be our last session before the reading week. So I made sure I have uploaded all the recording of the course up to today, and today I'll upload the lecture 18. So that would suffice for your midterm materials. So if you wanted to have a look the next week when you don't have any classes, you can just refer to that playlist. Also today. So today we're gonna conclude with the neural networks. The first Monday when you come back in 2 weeks, we're gonna have one lecture on CNNs, and then starting from the Wednesday, so in 2 Wednesdays from now, we're gonna start with the materials of your second part of the course, which are the complexity, the clustering methods, dimension reduction, and so on and so forth. All right. And as you know, your midterm will be in 2 Fridays from now, so March 1st. All right. So today, we're going to conclude with the implementation of neural networks. We've already discussed about forward pass. We already discussed about how we're going to calculate the loss function of that forward pass. We discussed about how we're going to converge to a local minima when we have the log loss or any sort of loss from our loss function using gradient descent, and later on we mentioned some variants like a stochastic gradient descent. So today we're going to talk about some other optimizations that are mostly recently were proposed, such as dropout. And also, after this, I'll conclude neural networks with a recap of all those different variants of a stochastic gradient descent. So I've already mentioned momentum before, but we have also 2 or 3 more that recently have been proposed and is being used. So if you are doing your projects, or later on if you wanted to work, at least you know, for instance, what atom, how atom does optimization, or for instance, how RMS prop does the job in this case. All right, so let's start with the dropout. So Jeffrey Hinton, in 2012, he found out in his paper that sometimes we are prone to overfit to our data set when we train our neural network. So why not we put another element of randomness within a model, and by just dropping out randomly some of the neurons and their interconnected edges. So it's as if you have such a model and you randomly pick these 2 that I highlighted and I crossed them in red, and you just leave them out. So later on when you leave them out, you're going to have a newer model with fewer neurons, and also at the same time fewer edges connecting them. And this would be done randomly in each iteration. And the results were remarkable. They have noticed, if you refer to the paper of Dropout, you see that simply by applying this very intuitive and straightforward technique, you're going to gain advantage in converging faster. So when you train your model, you're going to converge faster because it avoids overfitting as well. And also the choice of inactive nodes is done independently in each SGD update. So it's going to add even more, another element of randomness, because it's independent from each of the SGD updates. So a stochastic gradient descent updates. So thus, during backprop, when you're using that loss function to go back and update the weights using your backprop algorithm, only the weights connected to active nodes, right, are going to get updated. So it's as if we've dropped out randomly some of the nodes outside the model. All right. So, and during testing, also another advantage of using Dropout was during testing, we would use the entire network, but we would scale the weights by a factor of 1 minus p or minus rho, depending on how you're going to pronounce that. So, and normally this depends on your test model. It's going to vary. So it's as if you update your weights by a factor of 1 minus rho or 1 minus p, and then apply it to a network. So one of the sample usages would be that you have trained your model with a very large data set like ImageNet, and you want to test it on a very smaller data set, having the same number of classes, assume. So your model tends to overpower, and you're going to be overfitting to a smaller data set. So one of the advantages of using Dropout is during the test, you're going to scale the weights by a factor of 1 minus p. So say that p is 50% or 40%. And this will help you to avoid overfitting for that test case as well. So if you want to recap the advantages of having Dropout, it adds another level of randomness to your weights. So we don't have to rely on strong activations from few neurons. So at some part of the network, you're going to have some spikes because of that certain weights, and this could have had some negative points about your accuracy and also overfitting. So using this Dropout randomly, you might be able to just spot them and remove them. And it's pretty easy to implement, so it's very simple. That's why most of the modern models are having this. So this was P actually. So it's very simple to implement, and obviously it helps to avoid overfitting because we are adding another level of randomness to avoid that curve that we learned to completely maps to the training data set, right? Normally the recommended factor for Dropout is 50%, but I've seen other works playing with this hyperparameter to other in numbers. All right, so now we're just gonna recap with the variants of SGD. You've already known a couple of them already, so we're gonna just recap them all here for the sake of completeness. So the first one was the basic stochastic gradient descent that you learned right after a gradient descent, and it was because of its name you were generating your samples stochastically, so randomly from a distribution, and it would help you to converge to a good enough point with whereas the real or the default version of gradient descent would definitely converge, but this would add an iterative method to your basic gradient descent, and it would downsample the complexity of the convergence by a large margin, right? Because at each of your updates, the default gradient descent would have to take a look at all of your training data, and suppose that training data would be like millions and millions. So the order would be huge every time you iterate over this. And if you do it with the SGD, because it would just sample from 1, 10, or a number of batches from your training data, it would downsample the complexity of that. So, and we already learned that how we're going to apply the update. So the next W, WT1 in a vector of W, would be updated by the previous W, WT. That was the gradient, and that was the step size you had, right? And we learned that, suppose that was your curvature of E, and that was your X star, which was the global minima. So you would have started from this point, and you might have gone back and forth, but eventually you would go somewhere close to this. You might even pass that, but you would come back. So you would converge, sort of approximate towards this area using SGD, right? All right. The second one we learned was momentum. You would add another hyperparameter towards the direction of your global minima. So if you take a look at this pattern here, you see that your optimal direction is this way, given this 2D plot. So sometimes you're wasting your path by going left and right because you would want to go this way, and you have wasted by this amount. So if you break down in these two components, right? So momentum would help you to define another direction towards the global minima. Oh. Yeah, something is again. Let me restart this. Yeah. So you would define another vector called V of t, and you would have another hyperparameter called alpha. The alpha would adjust your previous W, your previous V, with the gradient and the step size, and when you were updating your W's, you would use this vector and its direction, because it's in a vector space, it has a direction as well. So you would directly better to your global minima, right? And we learned that momentum in most of the cases can be helpful to be applied with SGD as well. So now suppose you have a higher dimensional space and you want to make sure you're going optimally in each of those coordinates at the same time. Another variant of SGD came out recently with the name Alagrad, and it varies the learning rate across each of those coordinates. So depending on the location in your optimization curve, it would vary the step size at each of your coordinates. So at some point you want to go this way. So suppose you have it. This is only a 3D graph. So you want to go this way. So you have to vary this, bring it down maybe to that amount, a smaller amount, and make this one higher. So the learning rate could be varied here towards the optimal minima or the global minima, right? So they would do that by defining a C of t, a vector of C of t, which is updated by the previous CT minus 1, plus again the gradient of the weights and pointwise multiplication to this matrix. So it's as if you're doing it CT of j for, it's going to be the summation of I up to t, your gradient of wij raised to 2, right? Because you're doing a pointwise multiplication here. So now using this CT of j, we can update your weights. So this will be your updated W, your previous W, and this value would be added because of added grad, right? Otherwise, this would be the classic way we would update. So you will add this amount by a pointwise multiplication. And normally this is a very small constant. So in some literature you might find it by the name of delta or any other constant. So they would call it a very small constant, like 10 to the minus raised to the minus 5 up to 10 to a raise of minus 7 also. All right? Yeah. So it adds a small constant for stability. So now let's see the advantages and caveats of AdaGrad here. So obviously, if you're adopting or varying your learning rate towards different coordinates, so you're going to have the smallest step size along the steepest curves, because it varies depending on the gradient, right? So and this is sometimes very good, because if you take a look at the three-dimensional curve like this, and that would be your global point. So you're in the steepest step here. You don't want to miss and come from there to there right away, because you already passed the global minima, right? You want to make sure that instead of having this length, you want to increase it maybe to that amount and still go that way towards your next stop, right? So this point is much better than that one because it's closer with respect to that, right? So one of the advantages of AdaGrad was along the steepest curves, it would make the step size smaller, it would vary the step size. And thus it's very good it's a good convergence method for convex functions, obviously. And one of the disadvantages is in some cases the learning rate might vanish fast because depending on the shape of the comics, you might vary it to the point that it's going very slow and slower and slower. So you're seeing some vanishing in your learning rate as well. I mean, there are other methods applied to that, some other variants of ADGRAD recently. So they are constraining this limitation by some extent. But yeah, this is going to be outside the scope of our course for now. All right. Let's see the fourth one. I already just mentioned the name in our previous lectures, but let's see what it does actually. So it's called RMS prop. It actually uses least square methods. And the interesting point about it is it's also introduced by Jeffrey Hinton, but it wasn't in a paper. He was teaching in a workshop, and right at the session, he proposed, oh, why not we can test this. And by testing that, they found out, oh, they might gain some advantage. And after that, he publishes by this name, RMS prop. So it has its own history now. All right, so RMS prop, yeah.
What is the X symbol? Is that multiplication?
Yeah, it's a pointwise.
So like a dot product?
Yeah, so you have like these two matrices. So when you have this, you have to multiply this to that and then this to that. So it's a pointwise instead of the normal multi. Okay. Yeah, I'm going to switch it here. Point. Multiplication. Okay. So now you define a different C of t with a hyperparameter alpha multiplied by your previous ct minus 1 and 1 minus I of alpha, and then you apply a pointwise multiplication between your gradients of your weights, and this will become somewhere close to the previous one, but we learned, but it has some subtle differences. Again, you're adding a small constant for stability here, and that's again the pointwise. Okay, that would be your step size. So now you want to update your weight, the vector of W, WT1. So you would have your previous weight minus the step size. This is in the vector space, so the other direction of your gradients. Pointwise multiplication with that amount you calculated for C of t. And normally for hyperparameter, they vary this alpha from 0 to 1. So depending on the implementation and different scenarios, you might see different alphas. Okay, and to conclude this section, we're going to introduce the last one, which is called ADAM, or adaptive. I forgot the rest of the abbreviation, but the A stands for adaptive. And also, it's also been introduced in at U of T here. So our previous PhD student, and now he's an assistant professor himself, Jimmy Barr. So they basically took advantage of both RMS prop and momentum at the same time with some bias corrections. And so it's one of the fancier optimizers now. If you take a look at the paper, it has been cited more than 18,000 times in the past 3 or 4 years. So it's being used quite often recently now. Okay. So you basically define this CT just like the other two methods. You have one hyperparameter alpha to regulate that previous one with, again, this. But here you add another beta here and another vector. So if you recall, this vector was used in momentum, this vector was used in RMS prop, right? So they actually combine them two and add a bias correction. So it's the best of the two worlds. And then finally, you update your rate as your W plus T plus 1, previous W, plus this vector of Vt. So the vector of Vt, if you take a look at it, it depends on the Ct as well, and you calculate Ct from the RMS prop. All right, I'm just bringing back this graph from the Adam paper, just to showcase some of the performance measurements between these 5 techniques that you already know, and stop here. So this actually, was tested inside a paper Adam 2014. So you can Google it, using Google Scholar or other thing. So you see that these 5 different optimizers that you know, and in all 5 cases they have used Dropout as well. So if you take a look at the paper, in some of the results, they avoid using Dropout, and they show that using Dropout is beneficial. So by default they turn it on. So we have Adagrad, RMS prop, SGD. This is another variant of Adagrad, and the Adam itself. So you see that the convergence rate for Adam, in this case for MNES dataset, which was the hand digit dataset of numbers. So actually the performance here for Adam outperforms the other 4 in this case. There are other papers that suggest otherwise for other datasets. So in this case, we can just say that Adam was working better than the others. All right? Any questions for neural networks in general? Everything is good? Okay. So in this case, I'll conclude here. And hope you have a good reading week. Come back refreshed in 2 weeks and ready for your midterm. If you had any questions, just email me in the upcoming week. Okay, guys? Have a good day.